Hey, welcome back. As part of this session, we'll talk about data structures and algorithms and their importance. Also, we'll see the analysis of algorithms in terms of time and space complexity. Okay. So, yeah. So, data structures and algorithms are fundamental concepts in computer science or computer engineering. Any anybody want to become a software engineer, these are the basic fundamentals, okay, and which are actually very crucial to solve any application problems basically, and also it is very crucial to choose the right algorithms and all. And data structures are used to organize and store data in memory or disk. They provide a way to access and manipulate data in logical and efficient manner. Some commonly used data structures are like arrays, linked lists, stacks, queues, trees, and graphs. So algorithms are set up instructions or rules that define a sequence of operations to solve a particular problem. Basically, program also similar to this, a set of instructions to solve any problem. But algorithm will give the more optimized and performance. Those things will be included while defining any algorithm. Yeah, they can be used to search data, sort data, perform calculations, manipulate data in various ways. Some common algorithms are like a binary search, sorting algorithms like quick sort, merge sort, and graph traversal algorithms like a DFS, BFS, like that. In software engineering, choosing the right data structure and algorithm for a particular task is crucial to achieve good performance and scalability. For example, if a large amount of data needs to be sorted, choosing efficient sorting algorithms such as quicksort can significantly like reduce the performance time, processing time basically. Similarly, choosing the right data structure can reduce the memory usage and improve data access times. So, in addition to perform the considerations like data structures and algorithms can also impact the maintainability and readability of software code. Well designed data structures and algorithms can make the code more modular and easier to understand, while poorly designed ones can make the code more complex and difficult to modify. In summary, data structures and algorithms are important concepts in software engineering that can significantly impact the performance, scalability, and maintainability of software applications. Understanding these concepts and choosing the right ones for a particular task is crucial for developing high quality software. We'll talk about analysis of algorithms in terms of time and space complexity. Analysis of algorithms is the process of determining the efficiency of an algorithm in terms of time and space complexity. Time complexity refers to the amount of time an algorithm takes to solve a particular problem, while the space complexity refers to the amount of memory an algorithm requires to solve a problem. The goal of analyzing algorithm is to determine the best algorithm for a given problem based on its time and space complexity. Time complexity usually measured in terms of the number of operations an algorithm perform as a function of the input size. The most common way to express the time complexity is using big O notations, which represent the upper bound on the growth rate of the algorithm time complexity. For example, if algorithm with the time complexity of n means that the number of operations grows linearly with the input size. We will see with examples actually the time complexity. And space complexity is also usually measured in terms of input size. It represents the amount of memory an algorithm requires as a function of the input size. Space complexity can also be expressed with the big O notation, which represent the upper bound of the growth rate of the algorithm space complexity. In general, algorithms with lower time and space complexity are preferred over those with higher complexity, as they are more efficient and require less resources to solve a problem. However, the best algorithm for a given problem depends on the specific requirement and constraints of the problem, as well as the characteristics of the input data. In summary, analyzing algorithms is an important part of software engineering and computer science, as it helps to determine the efficiency of algorithm in terms of time and space complexity. The information can be then be used to choose a best algorithm for a given problem based on its requirement and constraints. Basically, the analysis of time and space complexity, if you know as a software engineer, the way you write code will be very optimized and also very efficient. So that is the reason this time and space complexity and choosing the right algorithm are very important in software engineering. Let us see how we can calculate the time complexity. Let us write one simple file and .cpp. So what I will do here is I will try to explain more detail about how the time complexity and big O notations can be calculated. We will see further all this analysis while working on the different algorithms like sorting algorithms and all. But for now, let's understand what is actually big O notation, how we can calculate um, uh, the time complexity basically. I'll write trying to write very simple thing. So what I will do here is I will try to write one function which actually returns a number of uh, loops or the number of loops it is actually or number of instructions it actually taking care. Okay. So what I will do now is I'll try to get it integer actually which is the number of instructions it is executed, and I will talk about uh, linear function. Okay, which actually takes integer n. Okay, and see what it will return. Just for understanding purpose actually what I will do is it will return n, right? So what I will do is integer res equal to 0 I will do. So inside that what I will do is I will try to add one for loop integer I equal to 1, I less than or equal to n, okay, I plus plus. Nothing it will do, it will just do res plus equal to 1, that's it, and it will return res. So what exactly I am doing here is to understand the time complexity of this particular function. So this is actually what it is doing. Whatever n you are passing to this particular function, this function go through the n iterations and it just try to execute this instruction that many number of times, right? Basically, let us see from the main function how it looks like, how to call and what exactly we are trying to understand that linear function. So what I will do is I will try to call this linear function n equal to linear function of 10. So if the output of this particular function is also 10, that means that the time complexity of this particular linear function actually executes n instructions n times basically, right? N times actually looping. That means the time complexity of this particular linear function is O of n, right? Let us say if n equal to whatever constant I passed, maybe I can define a okay. This n I am passing here. So if this n equal to 10 only, right? That only we are passing, trying to get it here. Yes. Um, we'll just try to do that linear function time complexity is n only. Big O of n. Okay. Okay. Let's see this. This will work as it is or not. Now what I will do is I will go to analysis G++. Oops. So I will try to run this function. Yeah, linear functions time complexity is big O of n only because it is running similar way, right? If you want to print what value actually n getting, n anyway we saw that n is 10. That's why it is executed this function. Let us see that one more function we will try to understand the time complexity of a quadrature. Okay. Okay. So what we will do here is basically RES. Okay. So I am trying to just explain like how easy we can understand this time complexity. Basically, it is very difficult to understand. So not very difficult, I can say. It is easy only, but logic we need to understand that. So what I am doing is one loop it will execute actually n times. That is what actually we saw in the linear. This is actually one for loop. It is a linear thing. Now what I will do is I will try to create one in nested loop that is equal to 1 to okay. So now what I will try to do is res is equal to 1. I want to see this nested loop how many times this particular result this particular instructions are taken executing. Basically what I am expecting is if I pass 10 here it will become like 100, 10 into 10. Okay, one for linear thing inside that actually this is for 10 times and this is also 10 times because we have, when where I equal to 1 the value will become 10 actually because when I is equal to 1 j will iterate into 10 times inside the loop, so it will become 10 at first time. When I equal to 2 again this will iterate for 10 more times, then res will become 20, so on. That means let us see like how it works actually. So now we can see that return res will do. Okay, now what I will do here is I will try to um, read this value using quad function of, and I am passing the 10 only here also, right? Okay, so now what we'll do is we'll see what is the value. If you know, right, n into n equal to n square, correct? N square, this you should aware. This is the minimum thing. Now let us see whatever the value we are getting m here. If m equal to n into n, that means this is the core exponential time complexity, right? So what we will do is we'll see this this quad function time complexity should be n square, right? N to the power of 2. We're going to say n square. Let us see this will print or not. Yeah, perfect. This is actually, if you want to print this value here, this will be kind of m is equal to 100, that is 10 into 10. Let us print and check it out. Okay. You can see that m equal to 100 and 10 into 10, that is 100, right? So that means this the big O of n square basically. This quad functions time complexity for this. Similarly, the space complexity also, depending on how much memory you are allocating, we can measure that memory also in terms of big O notation. Okay, that's it about this session. Thank you.